Thank you very much. Hello, everybody. So we are today in the electrification world. So we have more and more e-bikes around us. I'm sure that many of you has already driven one or own one, and those systems actually many of those requires torque sensing, and the reason is that the torque sensing is useful in the control loop, because when you apply torque on the pedal, the electronics can actually provide you the assistance that you need. And it's a very popular solution to use a magnetoelastic torque sensor in this context, because they are cost effective and they are non-contact. So you can measure the torque on a rotating element, such as the shaft. And today I'm presenting our last solution of a magnetoelastic torque sensor based on gallium arsenide all plates. And just to understand the working principle of this kind of technology, so this is mainly composed of two elements. We have a shaft, which is magnetized in the circular region, so there is no magnetic field normally coming out, and then you have magnetic sensors. And in this case, we are going to use all plates, gallium arsenide all plates, that senses the radial direction. And when you apply torque, actually you have a stray field coming out. So therefore, if you measure this output field, you measure as well the torque. The problem of this is that in general you have very tiny fields. So you have a few microtesla per Newton meter. So you need something very sensitive. And what we would like really to bring to this as a novelty. So if you, let's say the physics has been the same for the past 20 years at least. But we can find several solutions, so several attempts in the past where standard silicon all plates were used, but these were very limited because of the sensitivity, and therefore you find very impractical air gaps or the use of magnetic yokes to actually concentrate the signal. And then other options has been proposed, and the use of flux gate sensors, which became afterward, actually, we could say a quite standard way of implementing magnetoelastic sensors on e-bikes. Is what you find normally in the market. But they are cumbersome. They are relatively big. And so we propose to use gallium arsenide all plates to have a very compact solutions which overcome the limitation of the silicon all plates in terms of sensitivity and is more compact than flux gate systems. And how do you design such a kind of system? So first of all, the first step is to understand how the magnetic field is distributed. So you can model your shaft as a magnetic dipole when torque is applied, and then you can investigate what is the waveform of the magnetic field, of the radial magnetic field component on top of its surface. And if you do that, you can plot this line, which has these two peaky curves and correspondence on the end of the magnetization region, and then you can make some trade-off to understand where you would like to place your two sensors. And here, for instance, we place those sensors here, and those make a differential measurements among two parts. Why? As a trade-off among maximum sensitivity and let's say having more or less a linear slope, so that we are more robust against the axial displacement that the sensor may incur in the lifetime. And once you define your good, let's say, distance among your two sensors, so you are good to go. And therefore, we integrated the sensing elements. So actually, the architecture of the sensor is based composed of an IC in CMOS technology, which actually is able to measure in differential way two gallium arsenide all plates and make all the magic of the current spinning, amplification, filtering, of compensation, etc. And this is how it looks like. So we have put everything on a PCB 1 by 1 centimeter, in which you have your all the dies that are directly wire bonded. And this system reach a resolution of 20 nanotesla per square root of hertz approximately. And once you define your system, so you have your shaft, you have your sensor, and therefore it's time to test. So therefore we put actually our torque sensor solution, which is actually a shaft and sensor, to link two motors. So one providing a speed reference and another torque reference. So we can apply some braking and see how the sensor reacts. And this is actually a view of how this looks, an inset detail. So we acquire several parameters such as the length, the angle, and the let's say analog signal coming out from the sensor. And as well, we're able to change the axial position so that we can see what happens when we move the sensor. After this, we have a huge amount of data, and therefore it's time to make some figure of merit. So, one which is very important is the sensitivity with respect to the axial displacement. And what you see here, you see that this sensitivity has a pretty flat top, so it's like a bell shape. That means that you can actually displace this sensor by more or less 2 millimeters, and having a sensitivity change of 1%. So this could give actually the axial robustness. And another parameters in this system, so remember, this is a system as a contactless, and you have a rotating shaft and you have a sensor. So you have what is called the rotational signal uniformity error. So you have a residual error, which is due to the wobbling or spurious magnetization effect, that actually provides you an information of torque, even when you don't apply any mechanical load. But you see that it's pretty limited because we are bounded into this plus minus 0.5% over the full scale, considering a full scale of 200 Newton meters. And then we measure other parameters such as the linearity. So here we see that, for instance, there is a residual hysteresis and linearity error that we see from after linearization. And we can also use the linearized curve to extract the sensitivity of the sensor and compute convert actually the resolution, the magnetic resolution of the sensor into mechanical units, which gives actually this baseline of 0.1 Newton meter at 250 Hertz. As well, we tested in temperature, so having a residual error basically limited by a first order of chief compensation. And once we reach this point, then it's time to understand whether we are good or not. So, and how we do that? So we're engineers, so we like to compile tables with other and compare to other solutions. And here, I take the example of another magnetoelastic system, which you can buy, and another one based instead on strain gauge technology. And just to save discussion on the table, I prepared a couple of graphs. In this case, I compare the resolution at 250 Hertz against the range. And this star actually is the sensor implemented in our work. And those other lines are the other magnetoelastic sensor in the market and another one based on strain gauge technology. And we see that we fall actually already in a very good place. So we exceed the 9 bits of a noise-free resolution Pareto front. So we are doing better than other off-the-shelf systems. And if we see as well the error budget, we can compare actually our system with the others. And we see that we perform better in terms both on linearity and RSU with respect to another magnetoelastic technology. And we can also see that the strain gauge is the best one because strain gauge are very known to have very good linearity. And no RSU error for the strain gauge system because this is with contact. So there is no error dependent to the non-contact system. And so in short, this work actually showed how we started from a concept and tried to address one need, one for more compactness and increasing resolution of all plate based system, and how we get up to a prototype that has been tested in a laboratory. And there are still something that we would like to test. This will be part of future works to understand as well the robustness against other disturbances, such as, for instance, the bending. But what we can say today is that we have really obtained very good performances with respect to commercial system, the baseline. And we can also say that whole plates based on gallium arsenide could be a viable alternative against today cumbersome flux gate sensors. Therefore, that all plates could be readopted in magnetoelastic torque sensor. Thank you very much for your attention.